So, good morning. Let us start our lecture today. Um, um, so let me remind you how to solve differential equation using the integrating factor, right? So suppose that you want to solve x prime of t plus qt of xt is equal to ft, right? So the integrating factor will be that you're going to look at qt, right? So first you have to look at qt. All right, you're going to find a function qt such that q prime of t is equal to qt. So in this case, q is the antiderivative of the little q. All right. So q will be the antiderivative of q. So now you're going to multiply both sides with eqt x prime plus eqt qt xt, and this is equal to ft. All right. So let me explain the method again. Suppose that you want to solve a linear differential equation which is not homogeneous. In other words, on the right hand side, f can be non-zero, right? So what you do is you look into qt, and you're going to try to find the antiderivative of this small qt, and I call it capital T. And then I multiply both sides with e to the capital T, right? So this is eqt, q prime of t, and this gives me eqt prime. All right? And the whole thing, I'm going to use a product group, and I'm going to have here I have eqt. Eqtx prime is equal to f eqt. All right. So the whole method is simple. So once you after you find the function capital T such that the derivative of this function is equal to the little qt, then you're going to multiply both sides of the equation by e to the qt. So when you multiply both sides of the equation by e to the qt, what you get is e capital qt, small qt, but small qt is capital qt prime. So the whole term here will become the derivative of e to the capital qt. All right. So the left hand side you change this into eqtx prime, and this is equal to f e to the qt. So this is the so-called integrating factor method, right? Integrating factor. Now let us go back to our application last time of population dynamics. Population dynamics. So in the application, we have P, which is the population. dP over dt is rate of change of the population. And then we're going to have 1 over P, dP over dt is the growth rate. All right? So these are the quantities that we studied last time. So suppose that we have a population at time t. This population is like pt, for instance 100 million people. And then the rate of change of the population is the derivative in time of this function pt. All right? And the growth rate will be 1 over p dp over dt. So suppose that, so last time we finished at the point where we have, suppose that the growth rate is a constant, okay, and we have to solve the equation dp over dt is equal to k. All right? So last time we supposed that the growth rate is a constant. So the derivative in terms of p dividing by p is k. And then we have to solve the equation. dp over dt is equal to kp. All right? So this is a differential equation, first order and homogeneous. But we can use the integrating factor method. So you have dp over dt minus kp is 0. In this case, the capital Q will be minus kt, right? Because Q prime will be minus k. All right, so here, what you have to do is you look at the coefficient of the terms that do not have the derivative. In this case, this is minus k. So the capital P, now capital Q will be minus kt because in this case, Q prime will be minus k. All right? So you multiply both sides with e to the minus kt with p over dt minus kp. Then this is 0. Now you apply this formula, and you're going to have p e to the power minus kt prime is equal to 0. All right? So what is the solution of this equation? Yes? Yes? No? So what is the equation solution? Yes?
You would integrate both sides so you get on the left side that it's p times e to the negative kt, and on the right side you would get a constant.
Right. Can you sign the back of the paper, please? Thank you. So now to solve this equation, right? So this is a first order differential equation, but you have only one derivative. So what you do is you just integrate both sides. All right. So you have p e to the k minus kt will be a constant, right? Because the function whose derivative is 0 should be constant, right? So pt will be c e to power kt. K times t. Questions? It's clear? Right? So I explain again. So now I consider population. The rate of change of the population is, of course, the derivative, right? So the growth rate will be the derivative dividing by the total population. Now suppose that this is a constant, so you have dp over dt, 1 over p, should be a constant. I multiply both sides with p, so I have what dp over dt is kp. I put minus kp to the left hand side. I'm gonna get a first order homogeneous differential equation. Now I'm gonna use the scheme that I have here. The integrating factor will be exponential of something. So this something should be the antiderivative of the coefficient of p. So in this case, this is minus k. So you take the antiderivative, you get minus kt. So the integrating factor should be e to the power minus kt. All right. So then you use the formulation over there. You're going to have p e to the minus kt prime is equal to 0. This shows that p e to the power minus kt has to be a constant. So pt has to be c e to the kt. Right? So now let us go to the next concept, which is the doubling time. We have doubling time. So doubling time t0 is the time when pt0 is equal to p 2 times p 0, right? So the doubling time will be the time when the population is double. So I want to compute. We want to compute t0. All right. So I explain again. Now suppose that we have all of these formula in which in which the growth rate is a constant k. All right. Now I have to find a time when the population is double, and I want to compute precisely what is this t0. So how can I compute this t0? Right. So I have a population which is evolving. The growth rate is a constant k. All right. Now I want to know at what time this population is double. Yes.
You can take the initial population and multiply it by 2 and plug it in for PT, and then using the initial population, you can solve for the constant c.
Yes. Can you say at the back of the paper, please? This is excellent, right? So we have what? We have PT0 is 2 times P0. This is one equation, right? And the next equation that we want to solve to use this equation. So we have the size of the population at time t with this explicit formula. All right? Using the formula. So you have PT0 is CEK T0. All right? So, so now, again, using this formula again, you're going to have P0 is CEK times 0. All right? Which means that C is P0. Right? Now, so I explain again. So I use that formula. I replace T to be T0 and T to be 0. Right? So when I replace T to be T0, I'm going to have CEK T0. When I replace T to be 0, I'm going to have P0 is CEK 0, right? So here I replace T to be T0, and here I replace T to be 0. All right? So when I replace T to be 0 here, I'm going to get, this guy will disappear because it's going to be 1. Exponential of 0 is 1. Which means that here I have C is P0, right? So now what is T0?
Just T?
Yes?
Is it just T?
No. I want to know T0 so that P of T0 is 2 times P0, right? So here I know that T0 is this guy and P0 is this guy. So what is T0? Yes?
You could set the expression that we found for P of T0, so the C times E to the K T0, you could set that to 2 times C and then solve
All right.
for T0.
All right, can you sign the back of the paper, please? So I'm going to plug this formula here and I'm going to plug this formula here, all right? So PT0 is 2 times P0, which means that you have 2 times CEK T0 is equal to C. Now I divide both sides, all right? So let me rewrite again, right? So you have P T0 is 2 times P0. So PT0 will be C times E to the K T0. And this guy will be 2 times C. All right? You have 2 times PT0. PT0 is twice P0, right? But you know that by the formula, PT0 is C EKT 0, and P0 is C EK0. But K0 K0 is 1. So here I have C. So 2P0 will be 2C. So I'm gonna set them equal. Right? It's clear. Now, so what is the next step? I want to find T0. Yes?
We can find the infinite logarithm. We do the ln of both sides to get rid of to find the t value in the exponent.
Yes, excellent. So you're gonna divide both sides by C and you take the log, right? So you have EKT0 is equal to 2. Now I'm gonna take the log of both sides. So log of EKT0 is log of 2, right? Log of ekt0 is kt0 by definition, right? So kt0 is log of 2. So in this case, you're going to have log of 2 divided by k, and this is t0, and this is the doubling time. Right? It's clear? So I explain again. So the doubling time is the time in which the population is double. So the doubling time will be at time 0, such that the population at time 0, which is pt0, is double p0. So p0 is the initial time population. Now I want to solve this equation. pt0 is 2 times p0. I'm going to use the formula that I found here. P of t0 will be c times ekt0. All right? P of 0 will be c times ek0, but k0 is 0. So this is 1. I get c. All right? You have pt0 is twice p0. So I'm going to replace c ek0 on the left hand side and 2 ck on the right hand side. I have c ekt0 is twice c. I can remove c. I'm going to have ekt0 is 2. I'm going to take the log on both sides. I have log of kt0 is equal to log of 2. All right? Which means that kt0 is log of 2. I divide both sides by k. So t0 should be log 2 over k. So this is the doubling time, which is the time for which the population is double. Right? Questions? It's clear? Right, so let us do an application. So example. This is example 1.8.1. So PT is the population of the Earth, population of the world. All right. So the growth rate is 2% every year. So find the doubling time. All right. So suppose that we consider the population of the Earth. So PT is the population of the world. And suppose that the growth rate is 2% per year, which is not much, right? So, which is reasonable. Now you want to find the time for which the population is of the Earth is double. So what is this time? Yes?
Is it ln of 2 over 0.02?
Yes. Can you sign the back of the paper, please? So in this case, K will be 2%. And this is 0.02. Right? In this case, the growth rate, which is here, will be 2%, which is 0.02. So the doubling time will be T0 is log 2 divided by K, and this is log 2 divided by 0.02, and this is what? This is 35. Yes. So in every 35 years, the population of the Earth is double. This is a lot, right? Questions? It's clear? So this is a lot, right? So the population is double every 35 years. Right? So every 35 years, the population is double. Questions? Now let us try to find the cost of living time. Right? Suppose that so PT in this case is the cost of living. Now the next example, we're going to consider PT to be the cost of living. So the cost of living has an inflation rate of 5%. So find the time when the cost of living is double. Yes?
ln of 2 over 0.0205.
Yes. Can you say in the back of the paper, please? So in this case, the inflation rate will be this constant k that we have here, right? So in this case, k is 0.05, right? So the time t0, right? T0 will be log of 2 dividing by 0.05, and this is 14 years, right? So in 14 years, the cost of living is double, but in 35 years, now the population is double. So there are more and more people, and in a very short period of time, and the life is more and more expensive, in even a shorter period of time. Right? Questions? Clear? So example 1.8.2. So a population is triple every 7 years. We have to find the population. After 10 years. So in the next example, we're going to consider a population. We know that the population is increasing, is triple every 7 years. And we have to find a population after 10 years. Right? So in this case, we don't have the k yet. But we have to compute the k. Right? We don't have k yet. So the first step is to compute. Okay, which is the growth rate. All right. So here, I don't give you the growth rate yet, but we have to compute the growth rate using the fact that the population is triple every 7 years. So how can we, yes?
Would k be equal to the natural log of 3 over 7?
Oh, yes. Can you sign the back of the paper, please? This is a very excellent answer. Right. So now we have to find k. So the population at time t will be pt is equal to e to the kt c. All right? Yes, so log 3 over 7 is the correct answer. And this is how we compute that. So the population at time t will be pt is e to the kt times c. Right? So how can we express the fact that the population is triple every 7 years? Yes?
So it's the PT is P0 times E to the, and then ln 3 over 7 times C.
Yes. But, I mean, so how do you express that? I mean, how do you express the fact that the population is triple every 7 years? Yes?
When t equals 0, we can get p0 equals c.
Yes?
And then pt equals 3c.
Yes. So you're gonna compare P7 and P0, right? Can you say at the back of the page, please? So P7 will be e to the k 7c, right? P3, P0 is e to the k 0c. All right? You're gonna compare P7 and P0. So P7 will be e to the k 7 times c, and P0 is k 0 times c, which is c. So you know that P7 is 3 times P0, right? So after 7 years, the population is triple. So you know that P7 is 3 times P0, right? So which means that C E K 7 will be 3 times C. All right? So you're gonna remove C. You have EK7 is 3. So K7 is log 3. So K is log 3 over 7. All right? All right, so I explain again. The population at the time t is pt will be kt ekt c, and so you're gonna have to compute p7. So p7 is ekt times c, p0 is ek0 times c, and this is c. Because after 7 years, this is triple. So you have p7 is 3 times p0, which means that c ek7 is equal to 3 times c. You remove c, you have ek7 is 3, so k7 is log 3, so k will be log 3 over 7. Yes?
On a test, will we have to show how we found k, or do we just memorize that?
You can use this formula, right? Yes. But I mean, it depends. So if I don't say anything, you use this formula. If I say that, okay, you have to reprove this formula, then you have to do it. Okay. Other questions? It's clear? Right, so now we have a K. And now how can we compute a population after 10 years? Yes?
Plug the K that we found into PT, like to that whole equation, except change T to 10.
Okay, can you say at the back of the paper, please? So now you have what? You have PT will be CEKT. All right, so here you found K already. So K will be e to the log 3 over 7 times T. All right? So P10 will be e to the log 3 over 7 times 10. All right. Questions? Right, so from here we found that K is log 3 over 7. We want to replace K by log 3 over 7. So PT will be C e log 3 over 7 times T. All right? Now, to compute P10, I'm going to have to replace T by 10. So I have P10 is C times is e log 3 over 7 times 10. Right? It's clear? Questions? Right, so so this is an example in which you have to find the growth rates of the population, and this is not difficult if you know the solution of the equation. So now we're going to learn another thing, which is the U. So the U will be, so you have PT will be P0 EKT. Right? So because here we always find that P0 is C, you can write the solution this way. Right? So PT is P0 times e to the KT. So P1 will be P0 e to the K. Alright? So in this formula, I have PT is EKT times C. Right? But if you replace 0 here, you're going to have P0 is equal to C. So in this formula, I can write P0, PT to be P0 times e to the KT. So P1 will be PEK, right? So I replace T to be 1. So the U will be P1 minus P0 over P0. All right, the U will be the difference between P1 and P0 dividing by the original population, which is P0 e to the K minus P0 dividing by P0. So this is P0 e to the K minus 1 dividing by P0, and this is EK minus 1. All right? I explain again. In this case, you have PT is P0 e to the KT. You can compute P1 easily by replacing T to P1. The U will be P1 minus P0 dividing by P0. This P1 is P0 e to the K, so you minus P0 dividing by P0. You put P0 to be the common factor, so you have P0 e to the K minus 1 dividing by P0. So this gives you e to the K minus 1. Questions? Good. So this is basically the formula for U. All right? So example, this is example 1.8.3. So suppose that the bank has an interest rate of 5%. So compute the yield of the effective interest rate. Effective interest rate. All right. So suppose that the bank has an interest rate of 5%. Now you have to compute the yield. So in this case, what is so the yield in this case the effective interest rate. So in this case, what is K? Yes. Yes. Can you sign at the back of the paper, please? So K will be 0.05. Now, what is the effective interest rate? Yes?
The effective interest rate is the same thing as the yield, which is just d to the 0.05.
Yes, can you say at the back of the paper? Yes. So the yield will be, by the formula, e to the 0.05 minus 1, and this is what? This is 0.0513. All right? So this is a very simple example. Suppose that the bank has an interest rate 5%. So in this case, K will be 0.05. All right? So the yield will be the exponential of K minus 1. This gives you 0.0513. Questions? So now suppose that we have a more complicated system. So we have 1 by 1. Right? So here you suppose that the interest rate is 7%. All right? For 1,000. So every day, every year, the customer input 365 pence box. So find equation for the money in his account. All right. So suppose that the interest rate is 7%, and every year the customer put $3,650 into his account. Now you have to find an equation for the money in his account, right? Yes?
Is it, can I say the equation?
Is it what?
Is it, can I say the equation?
How do you write it?
I wrote it down.
Okay, so this is similar to the previous one, right? Except that you have to put something else into the population, right? So you're gonna call PT will be the money, right? All right. So this is similar to the situation when you have in the first example where you have the growth of the population of BC, and then you have people coming in, right? So how can we write this equation based on, yes?
3650 T plus 3650 times 0.007 T.
Can you say the back of the paper, please? So now if I call the money to be PT, right? So the rate of change will be d over dt of PT. All right? So if you call this population, this money, amount of money to be P, then the rate of change will be the derivative of P, right? So on the right hand side, you have what? You have 7%, which is 0.07. So you have 7. So the rate of change, the change, right? So you're going to have 0 plus $3. So every year, the amount is increased 0.07p because of the first one, because of the interest rate, right? So every year, the money will increase 0.07 times p, and then you put some money into the bank. So you have $3,650 dollars. All right. So this rate of change have to be equal to this one, right? So you have dp over dt is 0.07p plus 3605. Right? It's clear? I explain again. So every year, suppose that you have the money PT in the bank account. So every year, the money will increase, right? So the increase of the money. The money's. So this is the amount of the money this amount. Right? So every year, the money will increase 0.007p, and then you put $3,650 into the bank. So this is 0.07p plus 3,605 $50, right? So the rate of change has to be equal to this quantity. So you have dp over dt is 0.07p plus 3,650 bucks. Now, how can I solve this equation? Yes? So this is, what kind of equation is it? This is linear, right? Yes?
It's a non-homogeneous equation, so you can use the integrating factor method.
Yes. Can you sign the back of the paper, please? So this is a linear. So this is linear. This is non-homogeneous because you have something which is non-zero, right? Non-homogeneous. So to write it under the other form, you're going to have what? You have pt over dt minus 0.7 is 3,650. All right, so this is the form that we used to have. This is pt. This is ft. Right, so this is a linear first order differential equation with inhomogeneous input. Right, so the right hand side is not zero. So in this case, pt will be minus 0.07, right? So the equation that we have in the beginning is x prime plus pt of x is equal to ft. This is the first order linear differential equation, inhomogeneous, right? To solve this equation, we use the integrating factor, right? We use integrating factor. All right? So how can we choose the integrating factor in this case? So in the beginning of the lecture, right, we know how to solve this equation, right? So you have linear first order non-homogeneous. So to solve this kind of equation, you're going to use an integrating factor. In this case, we have the same. You have p prime minus 0.07p is 3,650. So this p will be the p here, right? The f will be 3,650, and p will be x, right? P will be x in this equation. Now we have every information that we have, and we have the method of integrating factor. So what is the integrating factor in this case? Yes?
We want to multiply both sides of that equation that we've written there by a factor e to a function q, and we want that function q to be a function such that its derivative is pt.
Right. Can you say at the back of the paper, please? So now we want to use this integrating factor. All right. So the integrating factor will be that we multiply both sides with the function e to the q, right? So the factor will be e to the q, but we have to know what is this capital Q, right? So what is this capital Q? You're going to look into this coefficient of the p, and you take the antiderivative, right? So qt will be minus 0.07t, since q prime of t is minus 0.07. All right. So this is a linear first order non-homogeneous differential equation. What we can do is to use the integrating factor. The integrating factor will be a function e to the qt, in which q is the antiderivative of the coefficient in front of p. So you look into this coefficient, you take the antiderivative, and this is the capital Q, right? In this case, the coefficient pt is minus 0.07. So q has to be minus 0.070. Right? It's clear? Questions? So now I multiply both sides of the equation with this integrating factor. So I have 0.07t times pt over dt minus 0.07p. And this is e to the power minus 0.07 t times 3560. Alright? It's clear? I expand again. In this example, we have some input from the outside, right? So the money is growing with the rates 0.07p, but you add some more money into the account. So you have to set dp over dt is 0.07p plus 3650, right? So if you put this guy to the left hand side, you're going to have dp over dt minus 0.07p, and this is equal to 3650. This is basically the equation that we consider at the beginning of the lecture, which is x prime plus pt, x is equal to f. In this case, x will be p. This pt will be minus 0.07, and this f will be 3650. So what we do is to use the integrating factor. Integrating factor will be function e to the qt such that this qt is the antiderivative of minus 0.07, which is minus 0.07t. Now I multiply the integrating factor on both sides. All right? So what I get is the following. So I have e to the power minus 0.07t dp over dt minus 0.07 e minus 0.70 p, and this is minus e to a 0.070 3650. All right? So what can we say about this guy? Without this guy. Minus 0.07 times e to the power minus 0.070, yes?
It's the derivative of e to the negative 0.07.
Yes, can you say at the back of the paper, please? So this is e to the power minus 0.070 prime. All right? So what you get is the following. You get e to the power minus 0t p prime plus e to the power minus 70 prime p, and this is 3650 e to the power minus 0.070. All right? I replace minus 0.07 exponential of minus 0.07 t by e to the power minus 0.07 t, and I take the derivative, I get this equation. So what can we say about the left hand side? Yes? Sorry? Yes, the product rule. Can you say at the back of the paper, please? Now you want to use the product rule, and you have e to the power minus 7t p prime is equal to 560 e to the power minus. Right? So you're going to use the product rule to change the left hand side to a derivative, which is the derivative of exponential of 0.070 times p, and then the left hand side and the right hand side will be the same. So to this step, how can I solve this equation? Yes?
Integrate.
Yes.
With respect to t.
Can you sign the back of the paper, please? So now I'm gonna integrate both sides. Right, so you integrate both sides. Integrate both sides. I'm gonna use the initial condition. So I'm gonna integrate this way. So I integrate from 0 to t of e to the power minus 0.007 goes from 0 to t, 3560 e to power minus 007s ds. All right? So I change the variable into s so that I can integrate. So the right-hand side, the left-hand side will give me e to power minus 007t pt. All right? Minus e to the power 0070, so which is 1, and then have p0. And on the left hand side, I'm gonna have 3560 e to power minus 007 s dividing by minus 007, and then I take the difference between 0 and t. All right? Now what I'm doing is integrating both sides, but because this is a population, I'm gonna give you the initial condition. So this is the initial amount of money, and the first s the time 0. So this is why I have to integrate from 0 to t. But you can do it the other way, it's fine. Now I'm gonna integrate from 0 to t, and I integrate the left hand side, which gives me exponential of 007t pt minus p0. On the left hand, on the right hand side, I have 3650 e to power minus 0.07s over minus 007, and I take the difference between 0 and t. So this gives me 350 e to the minus 007 t over minus 007, and then I minus e to power minus 07, which is 1, and then I divide it by 007. All right? Yes?
When you integrate both sides, I had a question. So that top equation there, when you're integrating from 0 to t on the left side, is the derivative of the integrand, is that derivative the derivative with respect to s or the derivative with respect to t?
With respect to s.
That's it.
Yes. So I changed the, so this is the derivative with respect to s because inside you don't have t anymore, right? I changed the name of the variable to s. So basically this is, right, so what the formula that I have is, right, so f prime of s, the s from 0 to t will be ft minus f0. All right? And the derivative is in s. Now, on the left, on the right hand side, I have to do this integration. I have 3560 exponential dividing by minus 007. I take the difference between 0 and t. The first one will give me this guy. The second one will give me this guy. So I have 3560 over 007, 1 minus e to power 00 minus t. All right? So I compute this, and I get 3560 over 007, 1 minus this guy. All right? So I'm gonna put 0 to the other side. So I have P007 T Pt is P0 plus 3560 over 007, 1 minus E007T. Now I multiply both sides with this guy. So Pt will be e to the 007 t p0 plus 3560 over 007 e007 t minus 1. Alright, so this is basically the formula. Right, so I did it correctly. So then let me explain this computation again. This is the equation that we have, alright? So what I do is I integrate both sides. When I integrate both sides, this is the left-hand side, right? So the left-hand side has to be a function of t. So when I take the antiderivative, so basically this is the antiderivative of this guy. So I have exponential pt minus p0 because the exponential at 0 will become 1. All right? So on the right-hand side, I have 3650. I integrate this, I get e. So the antiderivative of e to the power minus 0.07s is e to the power minus 0.07s dividing by the factor. And I take the difference between 0 and t. I replace t here and I replace 0 here. So I have 3650 e to power minus 007t dividing by minus 0.07 minus 1 over 007t. 007, right? Right, so I simplify this by putting 0.07 outside. I have 3650 dividing by 0.07, and this guy will become, so I have minus and minus, so this guy will become 1, and this guy will become minus, because here I have a minus, so I have minus e to the power 0.07t. All right? Now I'm gonna put P0 to the right hand side and I get this formula. And I multiply both sides with e to the 007t and I get e to the 0.007t P0. I multiply this with this guy and I get, so the constant here is the same. So when you multiply this by e to the 0.007t, you get this guy. Questions? This is basically the formula for the solution. Questions? It's clear? So this is a little bit of computation, but this is not difficult, right? Now, suppose that initially the customer has 1,000. So the money at the time T will be. So suppose that initially the customer put like 1,000 into his bank account. So what is the money at time T? Anyone else? Yes?
You take the formula that we found and you replace P0 with 1,000.
Yes, can you say in the back of the paper, please? So we're going to take this formula. The initial condition will be P0 is 1,000, right? So P0 will be 1,000. So the money at time T will be e to the 007t times 1,000 plus 3650 over 007 e to the minus 1. All right? So suppose that initially the customer has 1,000 in the bank account, which means that the initial condition P0 is 1,000. You only have to replace 1,000 here to the place of P0, and you have the formula for the money, the growth, so the total money after the time T, right? Questions? It's clear? Right. So basically, in order to solve all this kind of problem, what you have to know is the integrating factor method, right? The integrating factor. The integrating factor is easy because you only have to look into the equation and you look into the coefficient of the p or the x. Then you take the antiderivative, and this will be the q, and you take exponential of the q, then you get an integrating factor. Questions? Right. So let us go to another application. So population dynamics is one of the very first applications of differential equation. This is the simple form in which everything is grown linearly because we are solving linear differential equation, homogeneous or inhomogeneous. All right. So there will be cases in which you have system, a lot of equation, and then they are coupled together. In this case, you're gonna have a nonlinear situation. But we are not going to solve this kind of thing. What we are trying to do is to try to understand the next application, which is radioactive decay. So for a given atom of radioactive material, all right, there is a probability that it will decay. In a given period of time. Period of time. All right. So suppose that I give you a number of atoms of radioactive material. So there will be. So these atoms will be decayed. So you will lose some of them. And this is one example, right? One example is suppose that we have xt atoms at time t. Every year we lose 0.01 xt of this atom. So now I have xt radioactive atoms. They're decaying, which means that every year I'm gonna lose 0.01 xt. All right. So suppose that I have 100 atoms. After 1 year, I'm gonna lose 1 atom because those are radioactive atoms. So the difference in the situation here and the situation that we consider in the bank before is what? So what is the difference? Yes?
Well, in the bank, the money was growing, you're losing atoms.
Right.
So there's a decrease of.
Right. Can you say at the back, please? So in the previous case, the money is growing, right? So it's growing like 0.07% per year, and then you put money into it, so it's keep growing. In this case, you are losing the atoms until you don't have anything, right? So suppose that you have T atoms, and because they are radioactive, you're gonna lose some of them. So after 1 year, you're gonna lose 0.01 xt. All right. So what is the equation for this? Yes.
The rate of change dx dt is equal to negative 0.01 x.
Right. Can you stand the back of the paper, please? So you have the rate of change. The first rate of change is always the x over dt. All right. And the second rate of change will be minus 0.01 xt because you are losing atoms, right? So you're gonna have the x over dt is equal to minus 0.01 x. All right? It's clear? So in this case, you are losing particles, you are losing atoms. So you're going to have the x over dt is equal to minus 0.01 x. And so how can we solve this equation? Yes?
You also need the integrating factor to this one.
Yes. Can you sign the back of the paper, please? So this is going to be a first. This is going to be a first order differential equation with constant coefficient, but it is homogeneous because you have no input. So you have dx over dt plus 0.01x is going to be 0. So in this case, pt will be 0.01, right? So pt will be 0.01 and ft will be 0. So you're going to use integrating factor. Integrating factor. So what is the integrating factor in this case? Yes, can you sign at the back of the paper, please? So in order to find the integrating factor, you look into this constant, right? So this coefficient. So you have 0.01. So you integrate that. You're going to have qt, which is 0.01t. All right. You look into this constant, which is 0.01. So you're going to take the antiderivative of this guy. So you have 0.01t, and you take the exponential, e to the qt. So you have e to the 0.01t. All right? Now I'm going to multiply both sides of the equation with this guy. I have e to the 0.01t x prime plus 0.01 x. This is equal to 0, right? So e to the 0.01t x prime plus 0.01 e to the 0.01t x, and this is 0. So what can I say about 0.01 exponential of 0.01t? Yes, can you sign the back of the paper, please? So this is going to be the derivative of 0, e to the 0.1t prime. All right? I have e 0.01t x prime plus e 0.01t x prime is equal to 0. All right? That's good. So now what can I do? Yes? Yes. Can you sign the back of the paper, please? Now you're going to use the power of glue. So you have e 0.01t x prime is equal to 0. Right? So I'm going to use the power of glue, and the left hand side will be the derivative of this guy. So how can I? So because the derivative is equal to 0, what can I say about this function? So I have the derivative of this guy is 0. So what can I say about this? Yes? Yes, can you sign the back of the paper, please? So you have e 0.01t x is equal to the constant c. All right, which means that x is e to the power minus 0.01t times c. So x is times t. All right. So after you use the integrating factor, you can put the left-hand side under the form of the derivative. This derivative is 0, which means that it has to be constant, right? So which means that xt will be e to the power minus 0.01t times c. Questions? It's clear. So in this case, the solution is decaying, and in the other case, the solution is growing. So there are two different situation, but the solution is the way we solve it is the same. Right. So the half-life time. The half-life time will be time at the time t0, such that x of t0 is 1/2 of x at 0, right? So in the previous case, we have the double time. Now we have the half-life time. The half-life time is the time where the number of the particles, the number of atoms, is reduced to just a half. How can we compute this this t0? Yes?
We can plug T0 into the formula that we just found for x, and then we can also plug 0 into that formula to find x of 0, and so then solve the equation.
Yes, can you say at the back of the paper, please? So here, I'm gonna plug this formula. So I have e to power minus 0.0 t 0 times c, and for this guy, I'm gonna have e to power minus 0.001 times 0, which is 0. So I have only c. All right. So I plug t0 to be this t to be t0 in this formula. I'm gonna have exponential minus 0.01 t0 times c. I'm gonna plug 0 here. All right. I'm gonna find c. So now I have e to power minus 0.0 t0. C is 1/2 of c. All right. So I'm gonna remove the c. So here I have e to the power minus 0.001 t0 is 1/2. Right? So how can I solve for t0? Yes?
Take the log.
Yes, can you say at the back of the paper, please? Now I'm going to take the log, right? So I have log of e to the power minus 0.001 t0 is log of 1/2. All right? So on the left-hand side, I have 0.01 t0. On the right-hand side, I have log of minus 2. So why do I have minus log of 2?
What did you say?
Why do I have minus log of 2? Yes?
Because 1/2 is the same as 2 to the negative 1.
Right. So because you have what? You have log. Can you say at the back of the paper, please? Log of 1 over 8 is minus log of 8. Right? Log of 1 over 8 to the power k will be log of 8 to the, so our n will be log of 8 to the power minus n, and this is minus n log 8. Alright, so this is the formula. I take log of on the both sides. Log of e to the power minus 0.01 t0 will give me minus 0.01 t0. Log of 1/2 will give me minus log of 2. So then t0 will be log of 2 divided by 0.01. This is the half-life time. Questions? Right, so I explain again. So to compute the half-life time, I'm gonna have to solve this equation. X t0 is 1/2 of x0. So x t0 will be, I replace t0 here, and x0, I'm gonna replace t to be 0 in this formula. So I get exponential, this guy times c is 1/2 of c. I remove c on both sides. I have exponential of this guy is 1/2. I take the log. I have minus 0.01 t0 is minus log 2, so t0 is this quantity. Questions? It's clear? All right. So in general, suppose that that we replace the decay rate (0.01) by a number k. All right. Now suppose that I replace the 0.01 by a number k. What is the half-life time? Suppose that I replace the number 0.01 by a number k. Yes?
Ln to k.
Yes. Can you sign the back of the paper, please? So it's going to be the same, right? So here you're going to have xt is, here I'm going to replace this by number k. All right. So here I have k. So whenever I have 0.01, I can replace it by k. So here I have minus k. Here I have k. K. So here I have k. All right. So if I replace the decay rate by 0.01 by a number k, the solution will be of this form. You can check this. I mean, this is you just replace the previous solution. Wherever you have 0.01, you replace it by k, and the solution will be xt is minus kt times c. All right. To compute the half-life time, you're gonna have to solve this equation. But again, wherever you have 0.01 you're gonna replace it by k. So here I have k, k. Here I have k, k, and the solution is log 2 over k. All right. So this is similar to the double time one. Questions? That's good. So, right. So now I have one example. In 2 years, 3 gram of radioisotope decay to 0.09 K, 0.8 gram. So compute K. Right? Now we have 3 gram of radioactive items. In 2 years, it is decaying from 3 gram to 0.9 gram. So we have to compute K. So how can I compute K? Which formula is that I have to use? Yes? Can you sign the back of the paper, please? I'm going to use this formula, right? So I'm going to have xt will be minus kt times c, right? So, in the beginning, it has 3 gram. I have x0 is 3, right? In the beginning, it has 3 gram, and after 2 years, it reduces to 0.9 gram. So x2 will be 0.9. All right? Questions? Now we have to compute K. So we're gonna use this formula. I'm gonna have 3 is e to the power minus k times 0 times c, and this is c, which is x3. And 0.9 will be e to the power minus k times 2 times c. All right? So in this case, we're gonna use the formula that we have here, and I'm gonna replace x0 by 3 and x2 by 0.9. I'm gonna use those formula, and we continue this on Thursday.